Okay, so here we have notes for section 2.3, which is with continuity. So we've got your objectives, identify the intervals upon which a given function is continuous, remove removable discontinuities, and apply the intermediate value theorem. Okay, so here we've got continuity at a point. So it says that any function y equals f of x whose graph can be sketched in one continuous motion without lifting the pencil is an example of a continuous function. So y equals x squared is continuous because if I graph y equals x squared, I can draw the graph a smooth, continuous motion without having to lift my pen or pencil. So example 1 here says find the points at which the function f is continuous and the points at which f is discontinuous. So I'll break it up here. So continuous, and so these are two things that are opposites of each other. So if it is continuous, it can't be discontinuous, or vice versa. So discontinuities are actually easier to find. There's actually two of them on this graph. There's one here at x equals 1, and there's one here at x equals 2. Because if I'm drawing my graph, I have to lift my pencil at 1 to jump up here, and I have to lift my pencil again to go over that open circle and then continue to trace. So it's continuous everywhere else. So from 0 to 4, x not equal 1, x not equal 2. So wherever it's discontinuous, it can't be continuous. Okay, so continuity at a point. So an interior point is continuous if the value of the limit is equal to the value of the function. You have an endpoint if the at the left endpoint, if the right-handed limit is equal to the value, or on the right-hand side, the left-hand limit is equal to the value. So down here, if a function f is not continuous at point C, we say it's discontinuous, and that then is a point of discontinuity. So example 2, find the points of continuity and the points of discontinuity of the greatest integer function. So what the greatest integer function is, it's sometimes written one of two ways. It's either intx, or sometimes it'll look like this. It's referred to as the floor function. It rounds all values down. So if you look here, between 0 and 1, all the values are rounded down to 0. Even 1.99999, all rounded down to 0. So it's essentially the greatest integer function finds the greatest integer less than the one you're talking about, the number you're talking about. So 2.7, the greatest integer for that would be 2, because that's the biggest whole value less than 2.7. So this is continuous, discontinuous. So if you look at the graph, it breaks on every integer. So we can call that x equals k, where k is some integer. So it's continuous for all reals except x equals k. K is some integer. Okay, so down here, you've got types of discontinuities. So these, actually the same graph, oh no, sorry, they're not quite the same, are removable discontinuities. So this one here, you got a straight line, and then there's an open circle there, and then it continues on. Or this one, you have straight line, open circle, but there's actually a closed dot here. So the one point is moved up. So these are removable because I could redefine that point to fill in the open circle, or just redefine a new point to fill in that open circle. On the next page, we have the ones that are not necessarily removable. So this guy is a jump discontinuity. So you're going horizontally, then you jump up a value. So that was like from example 1 where the graph jumped. Infinite, the graph goes to either positive infinity, whoops, off the screen, up either to positive infinity, or it could go to negative infinity as well, but the graph spikes up or down. And oscillating, It's kind of hard to see on the graph, but that's where the graph starts to oscillate or bounce back and forth near the value you're talking about. So this has an oscillating discontinuity at 0. This has an infinite discontinuity at 0. This has a jump discontinuity at 0. So in all three of those cases, the location, the discontinuity would be at 0. Okay, so continuous functions on an interval, if and only if it's continuous at every point of the interval. So continuous function is continuous on every point in its domain. So it's a reciprocal function, y equals 1 over x, a continuous function. So if I graph 1 over x, it looks like this. So is it a continuous function? Now you would actually say no, because there's a break in it. However, continuous function is one that's continuous at every point in its domain. The value x equals 0 is not in the domain of this function. The domain of this function is all reals, x not equal 0. So since 0 is not in the domain, this is a continuous function. Because everywhere it exists, it is continuous. Okay, so combinations. This is just saying that if you have two different continuous functions, if you add them together, they are still continuous. If you find the difference, they're still continuous. You multiply them, they're still continuous. You multiply one by some new coefficient, k, still continuous. You divide them, still continuous, assuming that the bottom one isn't 0. So composites work the same way. So that's f of g or g of f, where you plug one function into another. If they are continuous, then the composite is also continuous. So example 4 says, show that the absolute value of x sine x over x squared plus 2 is continuous. Well, all three of the parts here are continuous. This function, continuous. The top is the product of two continuous functions. So it's using this rule here. F times g is still continuous. This one is just an equation, so it's continuous. And then you have the absolute value function as well, that they're plugged into, which is also continuous. So since all the parts are continuous, the whole thing is continuous. All right, and the last thing we've got here is the intermediate value theorem. So it says a function is said to have the intermediate value property for it never takes on two values without taking all the values in between. So, whoops, hit my camera. So what that means is if your y values range between some numbers f of a and f of b, that means it has to take every value in between f of a and f of b. So if y0 is between the two values, then you have some c that will have to generate that value. If you think about it in terms of like a real world, if you're driving your car, if you start in a parking lot and drive on the interstate, you're going, say, 65 on the interstate, there is some point along that drive where you are going exactly 37 miles an hour. There's no way for you to get to 0 miles an hour to 65 miles an hour without going through every speed in between. So that's saying there's some time at which you are going exactly some value. That's what the intermediate value theorem says. You can't skip over values. So example 5 says, is there any real number exactly one less than its cube? Compute any such value accurate to 3 decimal places. So saying, is there some number, x, that is equal to x cubed minus 1, one less than its cube? So I'm actually going to solve this graphically and let my calculator find the root for me. To do that, I need to move everything to one side. So I'm actually going to move everything to the right. So 0 equals x cubed minus x minus 1. I could also use a polynomial root finder as well. So if I graph it, x cubed minus x minus 1. Draw, looks like this, whoops. Zoom, not zoom. Oh, still zoom again. Window, initial, there we go. Reset the zoom. There we go. So there's my graph. So the solution is where it crosses the x-axis. So on a Casio, you can find that by pressing gsolve, F5, and then if you notice the very first option over here, F1 is root. So I press that and it'll automatically find it for me. So is there any number that is one less than its cube, accurate to 3 places? It's that x value right there. So x equals 1.325. It says to 3 decimal places. So that number is one less then it's cubed. So if I cube it and subtract 1, I should get the number back. So let's see if it works. 1.325 cubed minus 1. It's pretty close, 1.326. So I about get the number back from itself. That, I believe, brings us to the end of the section.